Alright everyone, welcome to discussion. So today we'll be talking about project 3A, which hopefully at least some of you would have looked at before coming to discussion. By the way, how many of you are still doing project 2B? Okay, none of you here. That's good. Alright, so project 3A, we are going back to Linux. So this will have no x86 component. A lot of you should be glad for that. But it's still going to be relatively challenging when compared to the stuff that you've already done so far. All right. Um, so let's look at what we are supposed to do here. Um, what we're going to do is we're going to build our own malloc and free, and we're going to do this by using a shared library. By creating a shared library. We're also going to have a contest. So towards the end of discussion, I'll be talking about like how the contest works and like what your exciting prizes will be. Okay. So for now, to get into it, we'll be actually creating our own malloc and free. We will not be replacing malloc and free with our implementation, but we'll be doing something on the side which looks very much like malloc and free. The reason we're not replacing malloc and free is because if you do that, I can reliably expect that all of you will be in office hours with like crashed computers. So we don't want to do that. We have enough of an experience with that, so we are going to just like have an additional malloc and free. Okay, so there's something that's slightly confusing about this malloc and free, which is that there's two actors who are managing memory in this current context. Okay, so first we have our operating system, which manages physical memory. So when you have a virtual page in your process, that's actually some physical page which has been allocated for that process by the operating system. Okay, so that part where the process asks for and gets some memory from the operating system can be done in two ways. Okay, one of them is the stack. If it's the stack, you just declare your variables, and whenever you declare your variables, that's going to be allocated for you by the operating system. The other is the heap. Okay, and this is where you can actually use where is it? mmap or sbrick to actually request memory from the operating system. Okay, so this is still at the level of a process and an operating system. Okay, so your process wants memory. It's going to ask your operating system. The operating system is going to take the parameters via the system calls or library calls mmap and sbrick, and then it's going to give you back a pointer to memory. Okay, so that's the first level, and this is the level that you don't have to touch. You're not actually going to do anything in the operating system. The operating system is going to work as it worked before. It's going to use these system calls to give the process memory. Okay, what you're going to do is you're going to do something on top of mmap and sbrick. Okay, in your programs, you would actually be, when you're calling malloc, you're actually calling a library function. Okay, just like when you're calling printf, you're not actually doing a system call, right? You're calling a library function which does write to the standard descriptor 1 on behalf of you. Okay, similarly, the malloc is also a library function which does mmap and sbrick on behalf of the user to the operating system, and that's why you're going to make a difference. So you will, instead of doing malloc, you'll be doing your own implementation of malloc, and you'll be interacting with the operating system to get memory for the user. Okay, did what I'm saying make sense so far? Okay, so in this project, we tell you what functions you have to implement. Okay, so mem_init is the part where your library is going to talk to the operating system and get a huge chunk of memory. Okay, so in size of region must be a multiple of the page size. The page size is going to be 4096 bytes, so a multiple of that. So it gets this huge chunk of memory for you. Okay, so that's going to be the first step in all the programs that you write. So or that we will write. Because this is a library, it strictly doesn't need a main. You'll be implementing all of these functions, but these will be exercised by some other file. Okay, I'll show you a demo to sort of like make this more clear, but I'll first run through what you're supposed to do. So mem_init gets the huge chunk of memory for you, and then all the rest of the functions are basically going to be managing this chunk of memory. Okay, so things that are disallowed in this project are calling the original malloc, calling free. Okay, so if you do things like that, you will pretty much get a 0. So all the memory management that's going to be done is going to be done by you using these functions. Okay. So once you have this huge chunk of memory, you might want to give some of it to a process, to basically your process. Your process will call memalloc some size, and then of the chunk of memory that you have already obtained from the operating system, you take some and you give it to this particular process. You say, here's the pointer to the memory that you wanted. Okay, so this will take a size. This size can be anything, but whatever it is, you must return something that's aligned to 8 bytes. Okay, so if they ask for size 1, a pointer of size 1, you should actually return something that's aligned to the 8 byte boundary. Okay, and then this just returns a pointer to the memory. So the calling process may just take that pointer and use that to fill it with whatever information they want. Okay, so we're returning a void star pointer. So as a standard practice, this can be cast by the calling process to whatever it is that it wants. Okay, so this should be familiar to you. Memfree is just our version of the standard free. We give it a pointer, and then the library will free that memory for us. Okay. So some semantics that you should be sort of careful about here. One is if the pointer is null, then no operation is performed. So free of null is actually legal in our setup. Okay. So similarly, if you are doing double free, that I don't know if you have actually written that out, but I think that should also be okay unless it's been reallocated to some other pointer. Okay. The important thing you should make sure to do here is coalescing. How many people know what coalescing is? Okay, pretty good. But for the people who don't know, so let's say you have memory which looks like this, right? This is 1 byte of memory, and then you allocate some memory, and then you have some. Sorry. Oh, forgot about that. Mm-hmm. Can you see so far? Visible? Okay. So you have your memory, and then let's say you're allocating things like this, right? So you're just like allocating 1 byte as you go along. And now let's assume that C, or let's do one more allocation, D. Let's assume that C is freed, and then B is freed. Okay. So now at this point, if we were to call our version of malloc with size 2, for example, we should be able to get that space. Okay, forget about the 8 byte memory alignment for now. For the simple example, don't worry about that. But basically, we have 2 free spaces in lines 2 and 3, and you should be able to actually allocate one chunk over the whole block. Okay, you shouldn't say I have 3 slots of size 1 each, so I can only allocate size 1 objects. Okay, so coalescing actually combines together adjacent memory locations into a big chunk of memory that you can send out to the process. So you could return a pointer to line 2 here, saying that that's a whole chunk of memory for you to use, 2 slots. Okay, and coalescing is going to be extremely important for you because that drives how much memory you can actually use, right? So to give you another example. So let's say memory looks like this, right? So we now actually have 3 bytes that are free in memory, okay? But based on, because the memory is fragmented, if somebody had asked for, I want to use this particular, I want to allocate a 3 byte object, you cannot do that right now, right? Because it's fragmented, you can't return 2 pointers, right? So there are various ways you can handle this. We don't require that you handle anything. So one way to do this is to compact, meaning you push D to 2 and then free to 3, and then now you have a big chunk of memory which you can then allocate. Okay. So for basic functional correctness, this is not going to be an issue, but for your contest, it might be. Okay. So another thing that you should sort of like think about when you have memory like this is, let's say I ask the calling process asks for a 2 byte chunk of memory. Okay, so I want 2 free slots. Now there might actually be, uh, let's say, many slots free in memory. Okay, you could actually allocate 9 and 10, 8 and 9, 7 and 8, whatever, right? So there are a lot of spaces that's available for you. So another thing that becomes important is, how do you find free chunks of memory? Okay, so you have memory like this, you must have some structure based on which you can tell which is free and which is not, and you have to search that structure to find out what's free and what's not. Okay, to sort of help you with this, we have a book chapter which is right here. So this is a chapter from Ramsey's book, and then he has a very simple sort of like way to do this. We already talked about that. Okay, so this is one way to sort of like do your own malloc library. So in this particular figure, let's assume that this is the whole chunk of memory that you have, that you got from mmap from the operating system. Okay, now you have to manage this and return some pointer to the user such that when you get that pointer back, you are able to free that memory. That's your job. Okay, so one way to do this is, you could have a header for each chunk that you allocate to the user. Okay, and this thing may have something like, size of the chunk that I have allocated to the user is going to be 20 bytes, and you have a magic number so that you know that whatever is in the size field is dependable, right? Otherwise, if it's just like random memory, if you read the size parameter, you will have some number. It will be cached some number, but you don't know if it's actually correct or not. Okay. So this is one way to do this. So this is a chunk of memory that you have allocated. This is where the pointer that you will be returning to the user. Remember that they can overwrite the pointer with anything that they can. If you return a pointer to here, your whole entry is going to be cleared off by the user. Okay, so this is a bug that you might run into fairly easily. So make sure you're returning a pointer to the sort of chunk of memory that they can use, and it should be a size at least what they expect, right? If they ask for 10 bytes and you return to them a chunk of 5 bytes, what do you think will happen? If there's memory beyond that 5 byte chunk that's allocated to some other thread or process, like then that's going to be a problem, right? So make sure that this is done correctly. If you give them, if they ask for 20 bytes, you can return more than 20 bytes, but it should be at least 20 bytes. Okay. So now that we have a header and a chunk, this is how you can do allocations. Let me see. Okay, so this is how it sort of like proceeds when you're using this particular approach. Okay, so right now you have 4096 bytes, you have allocated it from memory, and then you want to manage the internals of this chunk of memory. Okay, so you have a header which says, I'm going to have 4088 bytes that I can give the user. The size of the header is going to be 8 bytes. Okay, and then there's no other allocation in the system. This is the first time we're accessing this. Okay, now when we actually get some allocation, this is what you do. You're basically creating a linked list. Okay, so you're saying the first header would say, I'm going to have a chunk of size 100, and then the rest of it is going to be 3980. Then this would point to this. Okay, so that's where you find the next chunk of memory. I'm not going to this slowly and in detail because I'm going to expect that you will read this chapter and get most of it. Okay, so I'm just giving you a very brief overview of what's going on. So this is another picture of the same thing. We have 300-byte allocations, first one, second one, third one, and then we have the rest of memory. Okay, let me see. So, I mean, if you read this chapter, there's like a lot of things that you will sort of like get from it. One of the things to note is that there can be different policies in how you search for free space. You can just search for free space and find and return the first chunk that you get, right? To give you an example, let's say the user is asking for 20 bytes. and then you have a chunk, as you go through the list, you have a chunk of 40 bytes. Now you can return that chunk back to the user saying, use just 20 bytes of this. So that's one policy you could do, but you'll be wasting 20 bytes, right? Another policy you could do is, you could go through the list until you find something that's closest to 20. Like, is there just 20 bytes somewhere in the list that I can use and give back to the user, right? So that's another policy that you can do. Now, based on like what policy you use and how you're doing things, like you don't have to use a list. You can use different things in order to do this. Okay, list is just one of the methods possible. Based on what method you use, you will actually get different times for when you call malloc and when you return, right? If you have a huge list, let's say it has 1,000,000 elements, and you want to go one by one and check if it's size 20, imagine how long that will take, right? So one thing, I mean, if you want to participate in the contest, one thing to optimize for is how quickly can you do this, right? If I call a malloc 1,000,000 times, how long is it going to take for the whole thing? Okay, and of course we'll be calling malloc on free so that we fragment your free space. So how quickly can you actually find free space that satisfies our demands, right? So that's one part of the contest. The other part of the contest is if we give you a chunk of memory, let's say 1 megabytes, right? How much of that can you actually use fruitfully? So in this particular example, we are actually wasting 8 bytes here, another 8 bytes here, another 8 bytes here, and another 8 bytes here. So even though the chunk of memory we got from the operating system is 4 KB, we are actually only going to be allocate 4 KB minus 32 bytes to the end user, right? So another thing we will look for in the contest is, we'll give you a big chunk of memory and we'll be calling malloc and free all the time. Then how much of that 1 MB can you actually fruitfully use in your program? Okay, how close can you get? I mean, you can use all sorts of clever techniques to reduce the amount of space that you're using, right? So that's all going to be up to you, how you do that. And in fact, in the project, we actually give you some pointers, right? So one general rule in sort of software development is, if you know exactly the workload that will run using your software, you can make your software really fast or really space efficient, as it may be, okay? So we want you to learn that. So we have 3 different workloads in this particular project. So the first workload is going to be just all allocations and frees, of course, will be just 16 bytes. Whatever chunk of memory we give you, we will always allocate and free 16 bytes. Okay, so this is one big hint as to what kind of structure you might use in order to do it efficiently. Okay, in the second workload, we will be giving you 3 different sizes. That will be objects of, or like allocations of size 16, 80, and 256 bytes. Okay, in the third workload, you can actually have any size. We can call malloc your implementation of malloc with size 1, with size 1024, anything goes. Okay, so that's sort of a workload that's hard to optimize for. But the other two, you should, if you think about it, you should be able to optimize very to a large extent. Okay, because we're telling you exactly what you will get. So you don't have to handle, for example, in the first workload, you don't have to handle cases wherein like the object is going to be really huge. It's only going to be 16 bytes. So write your code keeping that in mind. Okay. All right. So let's see. So what else do you need to know? So in the rest of the class, I'll just be showing you some demo for it. Oh yes. Okay. So grading. So the way we're going to grade this project is, we'll have different tests for each workload. Okay. So for workload 1, workload 2, and workload 3, we'll have different tests. You're going to submit code for 3 different shared libraries corresponding to each workload. Okay. Now you are quite welcome to submit the same thing, but you will fail all the tests because we have different tests for different workloads. A sort of expectation is that for the first workload, you should be able to use a lot of space. The overhead must be really small because it's all going to be 16 bytes. Think about how you can use that. Okay. Whereas for the third workload, of course, you're going to be not that efficient because you don't know what the workload is, and our limits and what we'll be checking will be relaxed for workload 3. So remember that as you submit this stuff. But in the grading, we will only be checking for functional correctness. Okay, so we'll be allocating, we'll be giving you a chunk of memory, we'll be doing allocs, mallocs and frees and seeing if that works correctly. We don't care how long it takes. So that's just for the grading part. You can get full points just by doing that. Okay. Now for the contest, we care both about functional correctness and about speed and space. Okay, so there's going to be two workloads. So in the first workload, and you can submit different libraries for both. Okay, in the first workload, we only care about time and functional correctness. But the main focus is on time. How fast can you do thousands of allocs and free? So that's going to be the focus of that. In the second workload, we don't care about time, but we care about space efficiency. How much memory can you actually use if we give you, let's say, 1 megabytes? Okay. So we will look at we will look at how people perform on this, and the restrictions are there's going to be different contests for this section, and there's going to be different contests for Tyler's section, and there's going to be 3 winners for each workload in each section. Okay, so there can be 6 winners in our section, and the restriction on that is that this can only include 2 graduate students. We don't want the graduate students to be winning everything. Okay. So there will be 4 undergraduate winners and there will be 2 graduate winners, and all of this has to be distinct. One person cannot win 2 things. Okay. The prizes for this will be T-shirts, which we haven't designed yet, but we will soon. But we will have a T-shirt for each winner based on like their times. So look, we'll update you with the design of the T-shirts soon. Okay. So any questions before I go on to the yeah? Yes. The size will be 16. Size will always be 16. That's what it means. Yeah. Any other questions? Yeah. Sure, sure. Yeah, I mean, that was one of the feedback we got from a lot of students. So we are going to design our test so that we will do that. But to sort of give you a higher level point, you shouldn't be relying on the test that way, right? I mean, we originally are releasing the test so that like you don't submit and then you get a 0 because you did some silly mistake. The tests are just to help you at the last moment to see if your thing is correct, to catch silly mistakes. What we ideally want you to do is to design your own tests while you're coding, right? Have a test for every single thing that we ask for in the specification. So you know, even before we release our test, you know whether you're passing that or not. Okay, so that's what we expect you to do, but we will make it so that you can run one single test. Okay. Yes. No. No. You can only call memminute. Well, we will only call memminute once, and you should never call memminute any of your other code. Or mmap or sp. Yes. Good catch. Yes. Yeah. All right. So let me get to the demo part of it. I don't remember actually. It's not mentioned. Yeah, you can have a partner. All right, so let's get to this. So we'll be making a file called mem.h available to you. This is in 537-1/public. Okay, this is just the interfaces that you should should use while you're designing your libraries. Okay, don't change anything in this. If your library is implementing different functions, you will get 0. Okay, whatever library you're making, because you're going to be making a lot of libraries, right? All of them should have the very same interface. Okay, so I'll just show you a Makefile. So this is I'll walk you through the Makefile as to what anything does. Okay, so let's start from here. So you guys haven't seen what mem.c is. So So mem.c is basically a file which implements all our functions that we had in mem.h. Okay, so right now it's just a dummy file which has like compilable functions for each of the things that we want to implement. So this your shared library will basically look like this. It's a file which is implementing all of these functions. Okay, that's basically all your shared library is going to be. Now I'm going to show you how we actually compile this into a library. So first we have our mem.c, and then the first thing we do is we compile it into an object file called mem.o. Okay, so that's what this particular file is doing. The PIC is for position independent code. So this is going to be a library. So at runtime, we actually don't know where it's going to be loaded into memory. So we want to make it so that it can be loaded anywhere into still world. Okay. So we have our, so this is the first thing that we do. We compile our code into the mem.o. Based on mem.o, we are actually going to create a shared library. Okay, and this is the way you do that. You say -shared, and then the output of this is going to be libmem.so, and then to do this, you're going to actually use mem.o, and then we have the normal flags. Okay. And finally, your library doesn't have a main. Okay, it just has a bunch of functions that you're implementing. So main is going to be the file which actually is implementing this whole thing. Okay, and you have to use your shared library in there. So the way you do this is you say -l mem. So the convention is that libx.so will be referred to as -lx. Okay, here we have libmem.so. So we're just going to say -lm. Okay, the second capital -l tells us that you should find the .so file in the current directory. Okay, it's the path to the library. And then we're going to say the output of this is going to be main, and then the file is in main.c, and then the usual stuff. Does everyone understand the makefile? You're going to have to create a makefile like this because and you're going to have like a lot of lines for libmem.so or whatever because you're going to be creating a lot of different libraries. Okay. All right. So let's look at what main.c does. Okay. So in main.c, we include the mem.h header file so that we know what functions we are using. And then in main.c, we just say we're going to do mem init of 4096. So we're getting a page of memory. And then later on, we'll be doing things like mem down, mem alloc, and so on and so forth. So this is what some tester file will be looking like. Note that this has no functionality whatsoever. Okay, you shouldn't be writing your program so that you depend on something that's in your main.c. All of your functionality should be in your library. Forget that anything exists outside the library. If it does, then your thing will fail. Okay, and yes.
So main basically is what test code that we want to.
Correct, exactly. And you don't actually need to submit a main.c. So this is just to make sure that it's working for you guys. We'll be testing it with our own code, which will link with your library, and we'll do our tests. Okay? Questions so far? Okay? So, so one of the cool things about having a library like this, right, is that, so here, let me see. So here we see the different compilation steps that are going on. So the first thing that compiles is we have our mem.o getting created. Then next we are creating a libmem.so using mem.o. The third step, we link that into main.c. Do people understand how this is working out? So if you look at the linked libraries for your main, so we see that there's like libc, which is basically all your stdio.h and all of those things. And then we have our libmem.so. Okay, so we have successfully linked our file into main.c. Okay. Now one of the interesting things about dynamic linking, LDD, that's basically just showing you all your dynamically linked libraries. Okay, it's not doing much. It's basically looking at your code, and seeing where all of the different libraries that you're using come from and at where they're loaded into your process space. That's looking at your binary executable file, right? I mean, remember that if you did something like this, you can actually look at what's going on in your file, right? You can see things like there's actually something going on here. You have the libc init function, you have the libc some other init function which I don't know about. You have your actual main code. So if you look at the executable and if you, for example, do object disassembly, you can actually figure out all of the different things that the library is doing, I mean the binary is doing. So LDD is doing something like that to just tell us like where these things are loaded. Okay. Questions so far? Okay. So one cool thing here, and which will be depending upon to actually run our tests, is that you can change. Well, let me run this and show you, and then we'll do. So right now we have a hello world. It's calling mem_init, and we got a chunk of memory at this particular address, and then we call the memdump function, which does just this print and nothing else. Okay. What we're going to do is we are going to modify our library. We are not actually going to touch our binary or our main.c, and I'm going to show you how that actually changes your output. Okay, because it's linked dynamically, it's not static. All right, so let's just say to std out. Okay, so we say this, and then we say make libmem.so. We're not touching main. Okay, so we have only done compilation of mem.o and then libmem.so. Okay, now if we run main again, so we actually get the output. We are dumping all of memory to std out, even though we never touched main. Okay, so that's why we are calling this dynamic linking. At runtime, when you're running main, it will check for the latest copy of libmem.so because we tell it where to find it and what file it's called, and then it will link that into that main.c. So that's why we can change libmem without changing main.c, and we can still expect it to work. Okay? Do people understand what's going on? All right. So let's see. So I think that's all I have for this project. I do have some other things about the XV6 project I thought I'll go through. What did I call it? Okay. Okay. So what I'm going to do is I'm going to go through some of the faults that you had in XV6, and I'm going to help you see how you can debug such things, right? Because from what we saw on the 537 help mailing list, a lot of people had errors that were, you could see what is going wrong from the error message, but they weren't able to parse it to understand what's going on. So this is to sort of like help you with that. So a lot of you would have seen this particular error, which basically says there is a trap, and then it tells you nothing else. Okay, so I totally understand if you did not understand what this means, because I didn't at first glance either. But there is actually an easy way to figure this out if you run into it in your future projects. So basically, you go to you go to your XV6 code, and then there's a file called traps.h. This is what it's actually printing out when it gives that error. Okay, and it's basically saying we have an unexpected trap 14. If you go look at this. Okay, so it is telling you in its own way what's actually going on, just that it's very hard to understand. So what you need to do is then if you get this error, you go to this file and then you look up what 14 means. Okay, so in this particular case, 14 means a page fault. So hopefully this should give you some information as to how to debug your error. Okay, if you're getting 14, it's a page fault, and one reason for a page fault is it can't find where the page table is, or you're trying to run a process that's not been initialized, but for whatever reason there's something wrong with your process. So in terms of the scheduler project, one reason this came up all the time was because people are trying to run a process that wasn't even like properly initialized. They tried to run a reserve process, it was not there. They tried to run a spot process, it was not there. So they fix something out from the P table and they run it with predictable effects. Okay, so if you get something like this, this is how you go about doing it. For the second error, so for panic acquire, this should be more obvious, right? You're, you're getting this error because you're trying to acquire a lock that may have already been acquired. To give you an example of how this came about, in your scheduler code, you actually get a lock at the top, and then you loop through the whole thing, you release, and then you do the whole thing again and again, right? What some people are doing is they acquire the lock, and then they try to find a reserve or a spot process. There was no such process, so they loop again without releasing the lock. So then you try to acquire the lock again, and you'll get an error like this. Okay, so if you get an error message like this, it should really narrow your focus down to parts of your code which touch locks. Okay, don't look at anything else. There has to be a change in your code which does this stuff. Okay. Another error that we saw, hopefully this should also be easier than the trap thing, is you're getting an error which says implicit declaration of function get pinfo, for example. Okay. What this basically means is that you have a function and you haven't actually told the compiler where to find that function yet. You're using that function, but it doesn't know where it's declared, in what header files it's declared, or in what file the function is actually existing. So if you have a function in one file and you want to use it in another file, the way to do this is you have a header file in which you put the signature of the function, and then you include the header file in both files. That's how you communicate. If you don't do that, you will get an error like this, where it says, you have implicitly declared this function, I don't know where to find it. Okay? So that's one class of error that we saw. Another class of error, which is very related, is you have multiple definition of P in it, or next PID, for example. In this case, what's happening is that you have a function that's already been defined somewhere, that has a header file, that has a definition, a declaration, then you're re-declaring it again in your code. So, for example, something like this, right? So, let's say you include stdio.h, and then in your code you say what exit means, for example. And you say something like printf. Okay, if you do something like this, for example, then it will tell you that exit is being redefined, right? Because in the include file that you already had, I don't know if stdio has exit, but let's play along. But if your function is already has been declared in some other source and you're including that file, it finds that first. And so you're redefining a function that already exists. And so you'll get an error. Make sure that in your whole code base, you're only defining your function somewhere. You're just using include files to wherever you want to access that function. Okay, so that's one other class of error. Another thing that we saw was no page directory, which is very similar to the error that we saw before. If you're not actually doing anything related to page directory, and if this error sort of comes up, it means that you're trying to run a process which is not initialized. Okay, so it's an easy rule of thumb as you do more x86 projects. If you're getting an error unrelated to something you've touched, think about the process, or like what is common between that part of the code and what you have changed. Okay. Finally, if you're getting a segfault in whatever part of the code, a good reason might be you're accessing some pointer and you haven't checked whether that pointer is actually correctly initialized or not. Okay, so if you get a segfault, that should be the first thing that you should check. Did I just add some code where you're dereferencing a pointer, and if so, is it always guaranteed that the pointer will be valid? Okay. Sort of like a higher level meta point is that you should always write code incrementally. Okay, don't do like a whole bunch of changes and then compile and see if it works. You will spend a lot of time debugging. The way to do it is do a very small change, check that it works. Hopefully use some software like Git or SVN to save that version. Do an additional change. Okay, you can just copy files and say .version1, .version2, that also works. But whatever it is, keep multiple copies around. Okay, don't do changes and then like be in the position wherein you don't know out of like 10, 100 lines of code what is causing the error. Okay. Any questions? Okay, so that's it for today. I'll see you in class tomorrow.